So there you.
Okay, so welcome everyone again to our UNAV Journal Club. Today we have Nick Poovuttikul, hopefully I say it correctly, from Durham University. He's going to talk about holography and hydrodynamics with broken symmetry. So Nick, you have about 50 minutes.
Okay, thank you. So yeah, let me try that. I will tell you about mostly about this work that I did many years ago with Sasho Grossenov and Andy Lucas in 2018, and there's some application we used that in the paper earlier this year with a student in Iceland, Aruna Rajakopa, in my previous postdoc. So I say that I'm from Durham. I mean, I'm getting paid by Durham, but I still haven't been able to move to Durham yet since I start my job. But you know, these are small details in pandemic time. So okay, so here's the title, and I was told that this is informal talk, so I'm not gonna I'm gonna do a lot of things by analogy and not too many equations. So but if you have questions, feel free to find the answer. I mean, the problem here is that now I cannot hear your face, so having some people interactive at least vocally would be pretty nice. So okay, so this is a premise that I want to ask you. I want to tell you about. There's if you want to do ADS CFT, which I assume that you kind of already know a lot about these things. So I'm not gonna go through the details and derivation, but the first lesson we learned about holography is that, well, okay, if you have some global symmetry of some field theory living at the boundary or on the field theory side, then you can map it to the bulk, or for the gravity side, by making those global symmetry a gauge. More precisely, you have partition function with the gauge group with the background metric G, background gauge field A, and then you promote them to be the gauge field, the dynamical metric G, the capital G, and the dynamical gauge field A. So you make it into a gauge group, and they relate it at the bound to each other at the boundary. So we heard about all these things, right? So you guys are holography kind of ADS CFT kind of group, I heard. But I hope this is a standard thing that you have seen a million times already. Do I understand that correctly though?
Yes,
For sure. Yes.
Okay, then let me skip that. So okay, the point is that this idea has a potentially it's kind of correct, you play with different, you can try to do many things, given that the global symmetry map into the gauge symmetry, you can try to play with different gauge theory with maybe higher derivative terms or some DBI type action. It still has the same global symmetry, and then you can try to do the matching that and the experiment quote unquote, or field theory result of a generalization of a QFT. So for example, we know that the bona fide gauge gravity duality is n equal to 4 and at large n and infinite coupling. You can imagine exploring maybe finite n corrections or a field theory with different A and C central charge by adding high derivative term or the DBI term. Okay. And also you can try to do some phenomenological thing, mimicking IR thermodynamic of IR fixed point in condensed matter system or in QCD by these papers. You can imagine break the gauge symmetry spontaneously, and it's equal to spontaneously breaking global symmetry. And this is the famous holographic superconductor. You can imagine making a higher spin gravity, and which is dual to the ON vector model, where ON vector model has infinitely many higher spin currents, higher spin Noether currents, and it mapped into higher spin gauge field, which is gravity in the bulk. And this is also by Klebanov and Polyakov, and then by later more mutation by Garato and Yu. Okay, and you can also imagine changing Poincare algebra instead of using Poincare algebra in the bulk, you replace with something else. to get non-relativistic version of holography, or more precisely like the Kochava-Lipschitz version. So this idea has many implications, and I would it's and these papers are extremely well known. I mean, I think most of them has all citations in one paper that all my citations combined. So this is like a very amazingly good result, and it is used this idea that you use gauge, you map the global symmetry to the gauge symmetry. Okay, so yeah, well, so the plan for today is that why I just first want to explain why that statement that gauge symmetry become global symmetry in the bulk. Sorry, that global symmetry in the boundary become gauge symmetry in the bulk. That why this statement is clearly false. That's probably everything I've said. And then I want to motivate why I want to care about explicitly breaking symmetry, and then like some diagnostic of those, like how does it end has to do with hydrodynamics. So yeah, and I noticed that this might be slightly different than my abstract, but as a talk process, as I'm preparing the talk, this story seems to be more reasonable given the time. But is there any questions so far?
All good so far.
Okay.
No, it's okay.
Okay. But please do not hesitate to ask. All right. Okay. So why is this clearly false? Well, okay. First of all, gauge symmetry is not really a symmetry, so you cannot really break it. But global symmetry, you can break it either explicitly, spontaneously, or you can make it anomalous. And for example, anomalous symmetry in global symmetry has different manifestation in the bulk of holography, which is not the same as you gauging. I mean, you cannot gauge anomalous symmetry. If it is anomalous, you cannot gauge it. So it does this statement that you map a global symmetry to a gauge one. This sentence doesn't make any sense. And also, like if your symmetry, your global symmetry can be explicitly broken, but I mean, you cannot really break the gauge symmetry in the bulk. And okay, one particular example that people referring to is something called Enriso theorem. But let me actually mention this thing because it's a point that for confusion, at least to me when I was a bit younger, that when we say that like there's something like about Higgs mechanism that it breaks the gauge symmetry, but actually it's not true. Like, right? I mean, if you look at the computation that you do, you actually fix the gauge, and then you use a gauge field to eat like the number the goldstone, and this is like a procedure of gauge fixing already. But there's a procedure. I think there's some like already quite a few posts on Stack Exchange that explain like you can actually do the whole Higgs mechanism without actually breaking any gauge symmetry, or without choosing any gauge, and the gauge symmetry seems perfectly fine. So that's one thing on the basic example. The other thing is that, well, if it's a duality between like some field theory and some gravity theory, then what you want to do is you want to not only, you don't want anecdote like mapping gauge and like global symmetry. What you actually matching and want to match is operators like correlation functions, Hilbert space, 1-point function, 2-point functions, and gauge invariant operator, and precisely gauge invariant operator. So you map things at the gauge invariant, and Hilbert space doesn't see the gauge invariant. So what are we talking about when we say that the gauge symmetry become a global symmetry? So actually, it turns out that maybe a correct way to say this is that at least in the simplest example, we already have counterexample of the anomalous symmetry, right? You cannot even, you have to think about them in an entirely different way. But the statement should be that like it's a coincidence, but in most cases the symmetry group of the gauge symmetry in the bulk is the same as a global symmetry, as a symmetry group of the global symmetry in the boundary. And there is a map like using line operator and boundary constructions that discussed a bit by Halo and Uguri 2 or 3 years ago. Is this does this make sense to you?
Yeah.
This last sentence in particular, yes, it's very clear to me.
Okay, thank you. All right. Okay, so then let me explain to you like why do I care about explicitly broken symmetry, and it will be related to the questions like why why do I am starting with the global gauge symmetry duality thing. Let me. There's a few reasons why you should think about explicitly broken global symmetry, even though in classroom we focus more, at least in field theory classroom, we focus more on the spontaneously broken, which is arguably more interesting. But I think explicitly broken is also quite interesting in its own way. So actually, it turns out you can. It's not really mentioned this way, but if you look at free theory, and not only just free theory, but so integrable theory and then those kind of things, it has infinitely many conserved currents. So what does this mean? So this means that if you start putting that theory, free theory, and whatever in the box, and then I find a temperature, and then start checking it, and then look at the 1-point function of operators, and see like how it decays with time. I can plot the decay rate and put them together along this line. And then, at the bottom, I would see, conserved currents, where, it infinitely longly because of, not the theorem. And if it's a free theory, then I would just have pretty much like all the conserved current. Everything would just stay there the same as it is. Like there's no decaying, things just like move around forever. Kind of like, if I have a gas, I start shaking gas, if there's no interaction, gas is just gonna start moving and in the box and not doing much. If I start turning on interaction, like some perturbation, which you can do in, open some kinetic theory textbook, and it's not really mentioned in this way, but you can see that the operators, like the infinitely many conserved operators that you have in the free theory, it becomes explicitly broken. And so it gains some, decay rate if you put in some finite temperature. And for the one that dual to a black hole, where we can use a DSCFT to do computations, there's actually like a large separation. Usually the scale is set by temperature or chemical potential, which one is the largest. And then like the other decay rates are like the big separation of other operators that are not conserved and the one that are conserved. So there's a big separation between them. So you can imagine that like to go from free field theory-ish of perturbation theory to the one that is dual to a black hole. Maybe we can think of these like the lifetime or the hierarchies of operator lifetime as like a good indication whether which theory can be close to to the one that has a gravity dual. So this is one thing that this is why you might want to look at the operator lifetime, even though it's not belong to the concept to the unbroken global symmetry. Okay. Another reason is that, well, I mean, a system that is usually boring, most systems are usually boring without explicitly broken symmetry. But like, for example, you can imagine like the more fun example is maybe Maxwell theory. This theory has a so-called one-form electric U1 and the one-form magnetic U1. It's basically like a symmetry that counts the number of the Tooth line and Wilson line. And in the free theory, I mean, both of these things are conserved. So there's an electric flux that is conserved, a magnetic flux that is conserved, and the number of Tooth line and Wilson line does not change. But let's say you couple it to electrically charged scalar, of charge 1, for example, and then electric flux is completely screened. The Wilson line can now end somewhere, and the magnetic flux is conserved. So, and we could, I mean, I think it's not controversial to say that I think QED is much more interesting than just free Maxwell, and so this is one way to say that things can become more interesting when you explicitly broke in global symmetry. Is there a question so far?
No, so good.
No.
No? Okay. All right, then let me go back to the slide again. Okay. Now, then the question is that let me ask, like, how would one actually like break the global symmetry from the bulk? And there several ways to do it. And the most naive way is then, okay, well, there's like this gauge global symmetry duality thing. So can we just like add a new gauge field in the bulk and then break that gauge symmetry, whatever that means? Like, let's say adding some mass term to the gauge field in the bulk. That could work, for example. But actually, it turns out that this is not the only way to go. And there are many ways that the broken global symmetry can be manifest in the bulk. So for example, you can add the high derivative terms, which seems innocuous, like in the gauge symmetry become global symmetry paradigm, but it's actually not true. It does something else, and also some dilaton potential seems to be doing that also, and also multi-trace deformation is doing that as well. So I will present you like 3 or 4 examples where you can see where the global symmetry is. I'm not going to show you details, but I can tell you the result and like why it makes sense to understand these things as a implicitly broken global symmetry. Okay, so the strategy is the following. So given a holographic model, then hello, I can hear somebody open the microphone.
Yeah, Nick, may I ask you something? Can you go back to the
yes, please
previous slide,
please ask many things. Yes. This one or the other one?
That one, thank you. So
this one.
No, the other one, the next one about the how to break global symmetries.
Mm-hmm.
Yeah, exactly.
Yes.
So what about here regarding anomalies? That is another way to break global symmetries, for instance. Is it also possible to consider that case in here?
Yeah, I think, but that is this different ballpark. So I mean, like this, when I say implicitly broken here, I mean like badly broken by something else that is not in a control way. So anomaly is you are right. It's the broken of the global symmetry, but in a very specific way, and that you can compensate it by adding the topological term in the bulk. But it is a slightly different one from what I'm talking about here.
Yeah, okay. So you are interested here in breaking symmetry explicitly, right? So adding some terms that break the symmetry explicitly, but not necessarily coming from an anomaly or something like that, right?
No, not necessarily. Yeah.
Excellent. Thank you.
Okay, thank you. Yeah, we can talk about this afterwards about how you deal with anomaly, but I think this is pretty much much more well documented than what I'm gonna talk here. So okay, so let's say that the strategy here is that I will, if somebody give you a holographic model, then you want to check whether that global symmetry or the global symmetry dual to that holographic model is the same as the gauge symmetry in the bulk or not. And this is become quite difficult if you actually break the global symmetry. Sorry, if you imagine like that your global symmetry is explicitly broken, because like there might be no gauge symmetry in the bulk. So okay, it could be that you by hand insert some gauge field and you add a mass term to it later, but it could be that it's hiding in different guides that you didn't see it like very clearly from there, and these would be those examples. And and so you check whether, well, do the also like the other way. The other way is that it may seem like the bulk is perfectly gauge invariant, but you can check that the global symmetry is not the same as that gauge symmetry. But there is actually only one example of that I can think of. Another way, which is happen a bit more often, is that there is a hidden weakly broken symmetry that can interfere with the IR. So previously I told you that like the thing that dual to like classical GR black hole is the one where you have like bunches of operators that decay very fast and a conserved operator that decay very slow. But it could be that there are some other operators that like it's kind of like it's explicitly broken, the symmetry is implicitly broken, but there's some operator here. It's kind of hanging around on the same ballpark as the conserved current, and they can interfere with each other, even if the IR limit by omega over microscopic scale and k over k microscopic scale, which could be like a mean free path, for example, is much less than 1. So we can do both of these by comparing it with the hydrodynamics of the bulk gauge symmetry. So meaning that if the bulk symmetry, if your bulk has dynamical graviton, then you have a gauge Poincare symmetry, and then you want to compare it with the hydrodynamics with the only Poincare symmetry being a global symmetry. So you want to compare that and see whether are these statements actually hold. It would be a bit clearer with the example. But let me say a few words about hydrodynamics. By that, what do I mean? Especially relativistic hydrodynamics. So one can start like imagine you take some partition functions of a metric G and the background gauge field A. Background metric G, background gauge field A, it's invariant under reparameterization, and that implies conservation of energy momentum tensor and conservation of number. This is just the usual identity and it's not do anything fancy, but you can also write them like these things in terms of some proxies, which is it's roughly a conjugate of your conserved current. Like you can imagine temperature being the conjugate of energy, velocity being conjugate of momentum, and the chemical potential be a conjugate of the U1 current. So which are the conserved currents, conserved charge in this system, and then the background fields. And then the way you do it is you express T and J order by order in terms of these proxies by integrating expansion. So you write down the zero derivative term, and this is pretty much everything. There's only 3 terms you can write down. So J mu is a vector. So there's only one vector you can write down from these proxies and these fields. And for the tensor, symmetric rank 2 tensor, there's only 2 terms you can write. So this is all the terms you can write down. And then you can keep going like at each order derivative. So like I think for the parity invariant charge fluid, you have 3 more terms in first order. And then you can also go like to even higher order, and there's like a bit more terms. So like I think for charge neutral fluid, where J is 0 and you only have this thing, you have about 5 more terms in the, sorry, no, 1, 2. Actually, I'm not sure. I think it's about 5 more terms in the second order, and then the third order is about 20 more terms. But these number do grow, and then you can decide to stop somewhere. And this is like the recent development 1 or 2 years ago about the convergence of hydrodynamic series, and these were like the thing that people was asking about. But like for our purpose, okay, you decide that you want to stop, and then you write everything you can. And that's we heard many times before that this is a good model to a phenomenological model to apply to quark-gluon plasma or graphene or strongly interacting QFT. And the reason for this for it to work is related to and also like it matched amazingly well with the holographic result, and you can actually derive it from that. But so the reason for that is roughly following. Hello?
Hello?
We are here.
Yeah. You were still there. Okay. Thank you. I was hearing something. But okay, the reason for it to work is basically coming from this picture that that in the theory, strongly interacting theory, we believe that other operators that are not conserved currents, they're just going to decay very fast. And what is left and what is important is the conserved current, which is that these red part are the sector that is captured by hydrodynamics. And so you want to check like this picture may make more sense. Like if you have other operators that are, it's kind of like really broken and it interfere with the conserved currents, then hydrodynamic, you can check whether your hydrodynamic behave like it's usually did, or do you need to include something else to incorporate some effect that could be coming from like these other operators? And so this is like what one would expect. Yes. Yeah.
Sorry, I wanted to ask you a question. I mean,
yes, please.
I'm very familiar with the holographic expansions of the metric in terms of the standard Pfefferman-Graham form of the metric. Not, I understand that it's not useful for hydrodynamics, but what I understand that you make an expansion of the metric is a derivative expansion, but you can also think of in terms of powers of a certain scale, because in the Pfefferman-Graham form, the series is expressed in terms of powers of a scale, let's say ADS radius. In hydrodynamics, you understand that as a derivative expansion. But is there any scale that you can play with, that you can define in the system in such a way that you can expand in powers of this new scale?
Oh, like Pfefferman-Graham scale in those expansion? No, I don't think so. I think this is it's a different thing. So you can try to derive these expressions from gravity. And in that case, like, you need Pfefferman-Graham expansions in order to read off like the leading and subleading term near the boundary. But let's say, like, if you're familiar with I'm not sure whether people like read fluid gravity paper these days, but like there's like a series of paper by Rangamani, Hubini, and Minwala and company.
Right. Yes.
That they were deriving like exactly these expressions and also like bunches of other high derivative correction terms from there. And in that case, like you need to do two expansions. Like first you have like the bulk metric, you create and expand the bulk metric in the order that, it's kind of like, so you solve it order by order in gradient expansion, and you read off the coefficients. True. So these coefficients like epsilon plus p and rho, these you can read it off from the Pfefferman-Graham expansion. So it's a double expansion in that sense.
All right.
So that's why I don't think you can map them to one another, because you have to do both to derive this result.
Right. Thank you.
Okay. Thank you. Please feel free to ask any questions. By the way, I'm very enjoying the questions time at the moment. Thank you. Okay, so let's back to like, so what do the hydrodynamic predictions tells you? So on the level of the 2-point function or 2-point correlations, like these relations that you can use the standard trick to obtain 2-point functions of hydrodynamics, like, I don't know, Kardanoff and Martin or Landau and Lipschitz. You pick which one is your favorite. But once you do that, once you do this procedure, it will yield two kinds of massless mode. So for example, by massless mode, meaning when I take k to 0, omega is also equal to 0. But the first kind is this kind of mode. Omega is proportional to k, and then something minus I gamma k squared. Gamma is some coefficient, c is some coefficient. So this is something called speed of sound. A sound mode where c is the speed of sound. And so what these poles do is that it will hit the omega equal to 0 as I decrease k. And this is the complex omega plane. This is basically the poles of the 2-point function, or poles of the Green's function. You can derive this by like do the Fourier transform, the Fourier transform of these equations, and then try to solve them, whichever way you prefer. But this is I would just keep saying that this is like a poles of 2-point functions on the complex plane, which is something that you see in holography. Okay. Now, then, so this is like a sound mode, and the other one is a pure imaginary part, where omega is minus I dk squared, and this is called diffusive mode. So I told you earlier that you can see these poles in holography, and you can see like by just doing a small gradient expansion, like small omega, small k expansion. I'm not sure whether this is related to the previous questions or not, but you can also try to do small omega, small k expansion too. But I think to get 2-point function, you look at only linear perturbation level. So you can see, and people did see like these poles from the holographic 2-point functions, like back to for like Castro-Son and Steiner back in 2002, and you can also try to compute the 2-point function numerically, and what you would see is that you see not only just hydrodynamic modes, and then you also have like bunches of other poles that is has a real part, has but at k to 0, it has a finite imaginary part, or at the scale set by k. So you should like try to relate this picture to these things, or maybe not this, but more like these things. Like there's a large separation here that is set by temperature, and there's other operators and the concept currents. So this is like the part that's captured by hydrodynamic sector, and this is a part that it's kind of like microscopic, and this is like these are these other poles thing that it's not the red one. And again, this has been seen in holography since 2005. Okay, so well, then the rule of the game is that if your theory actually produce these poles, and that there's nothing anywhere near the vicinity of these hydrodynamic poles, then your theory is perfectly a class of bona fide hydrodynamics without nothing to modify. And so is that really the case? Let's look at that. So the first example is that what happened if we break translation symmetry. So the way people do this is that well, you add some ghost-free mass term to add the mass to the graviton, and this is there's something called like DRGT massive gravity, and the term that you can write down is that, let me charge my iPad just to make sure that it's not going to go down soon. Okay, so you first add these kind of mass term to in the bulk, that then where this k, let's see, where is the mouse? Okay, where this k, the bracket k is like trace of this matrix k mu nu, which is a square root of g, and some matrix f, which is it is something called the reference matrix. So it's kind of like it's a preferred matrix that you lock it in some frame, in some coordinate, and this is what give a mass to you give a mass to the graviton when you do a perturbation around like g equal to f.
Hey, Nick,
so people, yeah.
Can I make a question, but it's quite silly actually. If you want to do an effective field theory description, for instance, for a plasma doing this holographic hydrodynamics, how will you do it? Because if you go far into the infrared for certain plasma state, there are no photons, right? So
right,
yeah. How can you describe an effective field theory in terms of this boson Goldstone, this massless photon?
Without massless boson, well, very good. Okay, so I think like try to describe plasma with low energy effective theory with the massive boson. This is problematic for many reasons. But one way you can see this, maybe one way to do this is so this is probably the procedure, right? You identify what are your conserved currents. What are things that are conserved, and this is a global symmetry. So you can ask like, what are the conserved currents in plasma that you can like like plasma in the sun or those kind of things. Like what are the global symmetry that you have? And as kind of hinted here, then this is you have conservation of electric flux and conservation of magnetic flux. In the free Maxwell, when you have a QED in the plasma, electric flux is completely broken. It's explicitly broken. So, and it's kind of like you give a mass to the gauge field. So it's kind of a go out. But you still have like conserved magnetic flux. So one way you can do it is like in the same way as building like these kind of hydrodynamic but instead of you having a density, a U1 density, like a point of the object, you have like a flux density, which is a magnetic flux. So there is a paper, like I think in 2016, or sorry, not 16. What was that? When was that again? I don't remember. It has been quite some time already. Maybe I think in 2017. Yes, or 16, where the Grossanov, Hoffman, and Iqbal wrote like a hydrodynamic version of those things. And it turns out that plasma people have been like stumble upon this kind of thing for quite a while. And so it basically like boils down to this statement that you basically replace the number density by flux density. And if you do the expansion scheme correctly, you can match these things to each other. And this is something called like a theory of magnetohydrodynamics.
Okay. Yeah.
But there are actually many limits of a plasma. So the magnetohydrodynamic limit is when you look at only the conserved current, like basically in this picture, and you only look at the conserved current and not like other, almost like weakly broken symmetry. But for example, you can have like interplay between like a free photon and the plasma physics by like tuning whether these lifetime of these like kind of like weakly broken symmetry is like is it broken too badly enough or not badly enough. Then you can tune between the two, and you will see how this go in a bit actually.
Okay. Yeah. Thanks.
Okay. So this is the picture. Let me. Something is going wrong with my pen. I cannot seem to write it down. Oh, there we are. It is back. Okay. So okay, this K is this kind of metric, and you can it's clearly it doesn't look very healthy. This theory. I mean you kind of break diffeomorphism by hand through some of these choice. So okay, it is nice. You break asymmetry in the bulk, you break diffeomorphism in the bulk, and so you break translation symmetry in the boundary. So this go in the usual way. But actually, it turns out that there is an equivalent way to do this by using something called a Zuckerberg field. So you, instead of like breaking the symmetry explicitly with this field, you use a scalar field, where the scalar field is proportional to the spatial direction. So it's kind of like an axion, but not really. It's like more like a linearly dependent scalar field, which you can add. And I mean, this one looks kind of like horrible, these terms, but this is really simple. You just add a free scalar field with a non-zero derivative, and you can check that the equation of motion, like for choices of parameters in those two theories, that you can make them match to the equation of motion that become identical to one another. And the reason for this, that people back in 2013, when I started my PhD, was like kind of obsessed about. So, and what do you see? What do you see in this theory? What is that? So usually when you compute the energy correlation function, like these two, usually when you compute this thing in the charge neutral theory, what you see is that you're gonna see this pole, like this is a south pole, where omega and where because energy coupled to momentum, and because momentum is kind of like traveling together, and so you get this kind of mode, which is a sound mode. Here, when you actually break the translation symmetry, basically the momentum is no longer conserved. So when you look at the energy correlation function, the first thing you see is the energy diffusion. So energy, you put it energy, and it cannot it doesn't have momentum to take it somewhere else. It's gonna sit there and kind of spread out like through diffusions. And if you go further down you wait longer, you're gonna see some other pole, which is a momentum pole. But momentum is decay. So you inject momentum, it's gonna, without finite wave number, it's gonna kind of stay there, but it's not gonna stay there forever. It's gonna decay at some point. But if you increase the wave vector, like increase the derivative, then what you find is that these two poles come closer together, they collide and then they move on the side, and it becomes the usual South Pole that I claim that you would see. In case you don't believe me that this can happen, that this is a South Pole, the momentum, you can I can try to do something, make something more convincing. So this is the conservation of energy is this, right? Of px equal to 0, and then you have conservation of momentum plus dx of something of a pressure. So these are the two equations of when this thing is conserved, and when pi x equal to P2 pressure equal to delta P by delta E of delta E. Then you plug these things back in here, and you solve it, and you will find that there is it's a quadratic equation omega square plus minus c square k square equals 0 at the ideal order. Okay, so what is happening here is that you go from having a sound mode this picture on the south pole in the energy correlation. You split into like a pure energy diffusion, and with some possibility of like some other mode here that it will come together at some point if you go to high enough energy and hybridize, and it turn into the sound mode. You can understand this from this picture, that if you are around here at this energy scale or at this time scale, you're gonna see that this mode is like kind of like explicitly broken, and it has a decay mode. But I mean, if you make the lifetime of this guy much longer, and it will move further down, and you are at around this time scale or this energy scale, then you can barely tell the difference between whether like this one is a constant current or not. And so you kind of like in this case, when these two poles collide and then they move out, it was like your system is, it really an approximate symmetry that it's almost like the translation symmetry is restored, even though it's not. If you go to low enough energy, you're gonna see that the pole structure is actually different. Does this make sense to you so far?
Sure.
Okay. Now another thing, you're gonna see this picture a lot, but for different correlation functions. Now we can look at the high derivative in field strength at 0 density. So no charged black hole, just the normal Schwarzschild shield, but and you want to study the gauge field fluctuation on that. But now not on top of the Maxwell action, but like maybe higher derivative term. Or you can try to add infinitely many of them and wrap them together in a DBI action. So what actually happened here is that in the usual, and now unlike the previous one, where you actually start with the sound pole from here, you start with this picture. So you only have diffusive pole at some point, and there's no this blue pole anywhere if you have only just a Maxwell term. But as you crank up like the strength of the high derivative term, there's a new pole that's coming up, which is this guy. They will combine together, and then in exactly the same way, they come together and they move out. And you see this in the density correlation function. So what does this look like? It's similar to like the kind of sketch that I showed earlier. It looks kind of like the Jx or Jy become like approximately conserved. Because the reason is because of the following, because when I imagine that these two poles come together, they collide and they move out, I can imagine, I can try to capture these two poles with this sort of equation in this regime, where I have d by dt of jt equal to dx of jx and dt of jx equal to dx jt. It's kind of like this equation, like a solitonic number of some sort. And this is it has a kind of like a nice intuition is that if imagine you have let's say you go back to 1 + 1 dimension, so not on this thing, but let's say 1 + 1 dimension, and you have a conserved number of soliton, like a U1 topological symmetry and a U1 symmetry, then this system is kind of like integrable. And then when you create, it's kind of like when you create like some profile of a density here, and then it's gonna move around. You can collide it with the other one, moving this way, and then it's just gonna move past each other, and nothing is happening. There's no diffusion, so there's no colliding with each other or anything. So this is a situation, like the drawing one is a situation where you have both conserved solitonic symmetry and the usual U1 symmetry that are dual to one another. So this is another way to see this. And again, in this case, I just want to emphasize that there's no, some fake gauge symmetry that I have to add in the bow and delete it. It's kind of there. It is encoded there, and you might be missing this kind of pole that coming from higher derivative term if you're not scanning the parameter well enough, or you're not in this regime. But this pole is there, and you can check either analytically or numerically. Similarly, you can do the same game for high derivative gravity term. So absolutely no gauge field whatsoever. And for computational reason, you can imagine like a term like a Gauss-Bonnet term, or like the usual like Topf coupling term. But like that one is a bit more difficult. The latter is a bit more difficult to do computations with. But let's say for adding the Gauss-Bonnet term, this is like the Ricci scalar square, Ricci tensor square, and the Riemann tensor square. And people have been looking at like the spectrum of these things. So one of them, which is particularly interesting, is you look at the TTY correlation functions, which is the transverse momentum if the wave vector is in x direction. So in the usual hydrodynamics, what you're gonna see again this situation where you have a diffusive mode. So you start with only this thing in the usual hydrodynamics. Oh, sorry, with this thing in the usual hydrodynamic. And as you crank up the higher derivative coupling, there's a new pole that's coming up. And now they can exchange, they can come together and collide and move out in exactly the same way as before. And this you can play kind of the same game, okay? But like, so, when they move out, like what kind of operators that become conserved, like namely like, by the of something equal to 0 at when it has a zero spatial derivative. And in this scenario, it's actually the TTX that is become conserved. It's like, like a sheer part of the stationary tensor become conserved. And you can imagine embedding this thing into in this regime with the black regime. You can imagine embedding them into like some 3 index object which are symmetric. And you build some sort of like a higher spin 3 current. And this has this interpretation has some sort of nice appeal to the picture of like a free theory having infinitely many higher spin operators, and that all conserved. And then when you turn on interaction, all these higher spin become current symmetry. All these higher spin symmetry become implicitly broken, and then it goes away. And in this case, like it seems like you can try to crank up high derivative terms, but even though with by hand, but you bring up like these higher spin current back to life. Like so previously in the Einstein gravity that Cofton is starting at bit, there's no this pole is nowhere to be found. But turning it on and it will come back.
Nick, sorry for my ignorance.
Yeah.
So in 4 dimensions, the Gauss-Bonnet term is a topological term.
Oh, right. You were totally right. I screwed up.
Yeah.
It's 5. Yes. Yes, you're right.
Okay. Yeah. Now makes sense. Thank you.
Thank you. Okay. All right, so this one I didn't screw up the dimension, but this is a similar case to the plasma that I kind of told you briefly before. So the situation here is that you want to build some holographic dual to a plasma, where you don't have a conservation of number, so you don't add the usual gauge field in the bulk anymore, but you add like a two-form gauge field that will couple to the two-form current, which is kind of like that will become like the magnetic flux density. So it's a two-form object. So you can do that. You can add like these. You can add the first term, like this is the version of the Maxwell term. But it turns out that in 5 dimensions, where it will become like a usual for the electromagnetic, these current, like these two-form field has the following Pfefferman-Graham expansion. So it's a log R. So and there's a recipes of how you would do this, like in the multi-trace deformation, how you would deal with these boundary conditions. And the way you would do it is you add some kind of like double trace deformation. It corresponds to like the demanding double trace deformation term at the boundary, where this is like these things are roughly something like the current, the operator square, and these log something here. It's like the double trace coupling, which has it has kind of a Landau pole, but also like a finite part, which is playing a role of the renormalized electromagnetic coupling. But okay, these are terminologies. The point is that like I'm starting with a theory supposedly correspond to plasma that have only conserved magnetic flux. I don't even assume that there is an electric flux anywhere. I didn't assume that there is any electric field flux anywhere, but just a magnetic flux. So and that is the whole thing that I put in the holographic setup, that there is a background gauge field B, two-form gauge field B corresponding to the two-form current that become a magnetic flux. And yet when you compute the 2-point functions of this theory, what you will find is that in JTY correlation function, which you can think of as this is something like magnetic flux along the z direction, for example. Then I would have magnetic diffusion. So so you can ask, like, as I think somebody asked earlier, like what kind of like dynamical thing that you can still see, like you can still have a magnetic diffusion in the plasma, even though there's no gauge field, because precisely because the gauge field is damped away. You don't have a propagating mode, but you have a diffusive mode. So you have those. And then like if I tune these parameter here, which is like a double trace coupling, then there is a new mode, the new pole coming up, and then they can combine together and then they move out. This situation, this is as if the electric flux, the JXY, where J dual to B become a conserved current, and these two things is a spectrum of a free Maxwell theory. So you can actually you actually interpolate between the situation here is that you have conservation of magnetic flux, which is the genuine conserved current, and you weakly break the conservation of electric flux by this parameter, and that they can come together and they can combine, and then they move out and become like approximately a free Maxwell theory. You can also, I usually not gonna say this because it's kind of tricky, but since you guys are Chilean and Chileans importers of 3D black hole, but you can also do the same game for the Maxwell field in the 2+1b charged black hole. So, well, open questions. Then, is there like so I told you that there's many ways that you can see that implicitly broken global symmetry can manifest in the bulk. And clearly the broken geosymmetry and equal to broken global symmetry thing is actually not true. But it would be nice to have something like that. And I don't know whether like what I show you here, this is like the whole list of the whole thing, or is there anything more that one could add? Or maybe it's reasonable not to expect one. And there are a few theory approach, like hydrodynamic-like versions that are, kind of like hydrodynamic theory, but dealing with weakly broken symmetry. It is like a book in a book by Foster, and also Sean Hartnell and company like bring it back like a few years, like maybe 7 years ago already, 8 years ago. It's something called memory matrix formalism. But again, it's only true in linearized level. And so, and the other one is that, well, we see many examples, but it's kind of like they are weakly broken global symmetry, like in the system. So is there like a consistent way to derive a covariant equations for this broken symmetry? And you can see that here and there I have to pick components to see it more clearly. But like, you know, something like the generalization of fluid gravity map, but with explicitly broken global symmetry. So we know how to do it in some case, but there's no general prescription how to do that yet. So let me summarize of what I'm trying to say here. So like one thing that I want to emphasize is that it's actually important to actually to actually understand what are the global symmetry of your QFT that you're dealing with. And, you know, if you want to use the hydrodynamic as an effective theory, then you choose use the right hydrodynamic to the right symmetry. And then maybe you might want to be careful of weakly broken symmetry in holography, that it's not like if you don't put it in by adding the gauge field in the ball, it will never come to you. I mean, it can come in many shapes and forms, and mostly because, well, you know, there's no notion of like what do you mean by broken gauge symmetry? It wasn't there, and so the broken symmetry can exist and it can manifest in many ways. And yeah, this is pretty much all I have to say. Sorry for going slightly over time. And this is it. Thank you.
Thank you very much, Nick. This is the time because we were asking in the middle. So is there any question from the guys? Well, I can ask you something, but just out of my naiveness. If you have a broken symmetry that implies an anomaly, like you will have a word identity associated to that anomaly, will that anomaly affect the transport coefficients of the boundary fluid?
Yes, actually, it turns out that it does. So you can, let's see, okay. So you might want to ask like whether like how these things affecting, you know, what is a holographic manifestation of anomaly, and that you can see it from it will become, let's say, okay, let's say like the usual anomaly, like the U1 anomaly in 2+1 in 1+1 dimension, and its corresponding fluid is Y+1D fluid, you know, Y+D fluid living in 2+1 dimensional gravity. So it would be like the usual BTC stuff plus the Chern-Simon term.
Yeah.
So it's just that, and then you can compute the transport coefficients with that, and you will find that there's some coefficients that wasn't there in the usual fluid, but that is now appearing, and it's fixed by the anomaly coefficient. So this is like what you see from gravity side. Now you can ask, okay, whether do these results actually depends on my choice of gravity theory, and it turns out that it's not. So it is like you know, these Chern-Simon term in the bulk, this bulk gravitational Chern-Simon term, not gravitational, like the Chern-Simon term in the bulk is playing a role like it's only making anomaly inflow to the boundary in the same way as the way that people in quantum Hall were doing. So it's not actually interfering. So but it's a different interpretation that, you know, it creates some transport channel that it wasn't there before.
Okay.
So this is on the gravity side. Now on the field theory side, there are several arguments that you can use. So you can compute like in the brute force term. You know, you can if you have a free field limit, you can compute it you know, these transport coefficients, and then you say you use some non-renormalization argument that okay, it's true in the 3 levels, so therefore it has to be true because like anomaly is one loop exact. So that's one. The other one, there are several other approach that you can also do. The other one is that you there is a conflict between having this anomaly term and a positivity of entropy production. So when you try to build like the entropy functional, then with the anomalous Y identity, then you'll find that the entropy can actually decrease with time, which is it's not really allowed. So it's kind of like by demanding that entropy cannot decrease with time, you put some constraint on the transport coefficient by equating it to anomaly coefficient. So this is a paper by this guy Son and Surovka. Okay, so I think it's 2008 or something like that, or 2009. I'm sending you to the link in the chat.
Thanks. Initially for
okay, so
yeah.
But this is like the usual chiral anomaly. There's like a shit tons of other kind of anomaly. Sorry for you still recording, right? I say a lot of shit already. But there are other kind of anomaly, like discrete anomaly.
I guess Felipe can stop the recording.